Is the recording okay? Yep, okay. Hello. I am here to give the presentation on the metal organic frameworks and their application to catalysis. So, firstly, I will talk briefly about myself. I come from Hong Kong. I grew up in Hong Kong, and then from 2016 I came to Trinity to study study the undergraduate degree in chemistry. And then after 4 years, after a very hectic 4 years because of also because of COVID, then I started my PhD in inorganic chemistry, also with Trinity College. So a little bit on the difference between the college and the Department of Chemistry, where the research is mainly based, is that the college provide, as Richard previously mentioned, some support, and then there is also the accommodation, and there is also some food, and then where your tutorial classes are, that is the small classes, like the 1 to 3 or 1 to 4 classes that are in the college. And then there are also lectures, there are labs, teaching labs that you learn how to do some certain experiments. That these things will be in the Department of Chemistry. So that's the difference between the college and the department. Now, about metal organic frameworks. So what are these things? So this is some things that is formed from metal oxo clusters, which are ranging from oxidation state of 2 to 4. And then also they are joined with organic linkers that are held tightly together by the electrostatic force. It's a little bit like these sort of ball and stick models that you can buy and in order to build whatever structures that you want to. It's just that the balls and the sticks are different. They are chemical balls and sticks. They are around 10 to the -9 or 10 to the -10 meters of order of magnitude. So really, really small balls and sticks. And in this case, this is actually a structure, an atomic structure, where you have these zirconium oxo cluster. In my case, that you have the red spheres being oxygen, and then the black ones are the organic linkers, are the carbons. So these are joined, the organic linkers joining these sort of atomic balls and to form this giant structure. So if we look at the periodic table, these are the metals that we work with. Would you guys be able to see? Oh, where can I get a laser pointer? Pointer? Yeah, there we go. So these are the metal bits that we care about as to use these sort of metal organic frameworks. And then the organic part obviously would be based around carbon. And in my case, in my research, the organic linker I use is called a terephthalic acid, which is this molecule over here. So catalysis. What is catalysis? Is this point that we are starting the survey. How do any of you know what catalysis is? Please feel free to go onto the software and then and see what catalysis is.
Okay, so I would just clarify, the poll is open, the word cloud poll. What do you know? What is catalysis? What do you know about catalysis for your A-level syllabus?
Do I have to log into the software as well in order to be able to see the answers?
You don't, because I can also present it. I can present it. There's nothing entered in the poll yet, but I will put it up as soon as it's there. Would you mind if I interrupted you as soon as anything goes in? Okay, you fire away. Go on. Sorry, would you like me to show you?
Yeah.
Well, I'll just interrupt you and read out anything as anything emerges, if that's okay.
Sorry.
Yeah.
How? Sorry, I'm not very entirely comfortable with technology. I need to find. Oh, right, there we go. I found my presentation again. Right. What is catalysis? So essentially, we are trying to lower the activation energy barrier. That's the A-level definition of what catalysis is. So realistically, when we try to do the catalysis, bit, there's the homogeneous and the heterogeneous catalysis. They are split into these two different categories. So homogeneous catalysis would be when your reactant and your catalyst are of the same phase. For example, they may be same, they may both be liquid, or they may both be gaseous. On another hand, heterogeneous catalysis is what I am focusing on. The metal organic frameworks that are used as a catalyst would be solid form, and then the reactions we are trying to catalyze would be of gas phase or liquid phase. So this graph that I'm sure it's in the A-level syllabus, you draw this activation energy barrier, and then you say, oh, because of this catalyst, the energy, the activation energy can be lowered, and as a result, you have an increase in rate. So some good examples of catalysis is, for example, the Haber process, which can generate ammonia from nitrogen and hydrogen gas. So these sort of reactions are done with an iron oxide catalyst, and that's how the reaction is done, and that's how ammonia is produced for fertilizations or any sort of related products. Now, in these sort of heterogeneous catalysis, as previously mentioned, I would be using the metal organic frameworks as stuff in order to be as catalysts. And these are some of a selection of reactions that our group investigates. One of them is the CO2 reductions. So CO2 reductions, there are a range of different products. Methanol is one of them, and there may be methane in order to, for example, regenerate the fuel, the fossil fuel, or maybe natural gas for both those sort of applications. And then there's also water splitting. So water water to hydrogen. This hydrogen can also potentially be used as fuels. And then there may also be polyethylene degradation. So at some high temperature with some catalysts, we may be able to regenerate these sort of polyethylene into their monomer, the ethylene molecules. So,
Bryan, sorry to interrupt. Just to say that on the poll, reduce activation energy was one viewer's response.
Yes, well done. That was exactly the book definition of what catalysis is. That's great. Thank you very much. And then in order for us to we need to overcome, because that activation energy barrier was lowered, we still have an activation energy barrier, and normally go through that activation energy barrier. So one of them is by temperature. So we may use at really high temperatures for some really hard reactions. For example, in the case of polyethylene degradation, those sort of carbon-carbon bonds inside those materials are quite strong and therefore need very tough conditions. On another hand, there are less tough conditions. We can use the electricity, which is called electrocatalysis, and this is called for temperature, that's called thermocatalysis. This one would be light, and that is called photocatalysis. This is actually the sort of catalysis that we work. So what I work on, so it would be similar. You have all your ingredients in your beaker, and then you shine light onto it, and then you measure whether there are any interesting products that you can see from your beaker. Right. So why MOFs? Why do we use metal organic frameworks for these sort of applications? There are two advantages. So there are this is the porosity. It has a very high surface area. So these your molecule, in the liquid or gas phase, they can diffuse into the porous nature of your MOF and then do your reaction. And then also the chemical stability and tunability means that we can change a lot of things structurally in order to understand whether there are any advantage, how they can help with the catalytic rate. Now, regarding this chemical stability, this UL66 is the sort of MOF that I'm working on, which uses previously this terephthalic acid as the organic linker. So what I have done is I've changed this linker to introduce different functional groups. For example, this is the amine group, and then this would be a bipyridine functional group that they just have different names. And then with the balls as the zirconium oxo clusters, I can make these sort of linkers, MOFs, which this sort of giant structure would be able to incorporate these sort of functional groups into the morphs. That's what we mean by the kind of the structural tunability that we can use for further reactions. Now, exactly what I'm doing in my research, pretty much between these three things. So synthesis, I would go and make the morphs and then maybe do things with it. So introduce different functional groups, as I previously mentioned in the last slide. And then I would do some catalysis on these sort of things, on these sort of newly synthesized materials, and see, oh, for example, this change I have made in my synthesis procedure actually improved the catalysis rate. And then I need to do some characterization in order to find out why the catalytic rate is improved. And then if not, if the catalytic rate is not improved, maybe there are 6 other things that I need to try. Or if I'm unable to characterize well, I may need to try some catalysis reactions with different parameters. For example, I may need to take out one element, or maybe I need to add other things into it and see how it affects the catalytic rate. And then if the characterization comes out to have a good story of explaining, oh, for example, this factor would facilitate the higher catalysis, is there something I can further do in order to improve it? Then I may need to go back to the synthesis part. So I may need to make new things. So you kind of just roll over and cycle between these three things. That's mainly what we do as research. So the synthesis part, I'll just briefly mention these. So it's kind of just like shake and bake chemistry. So what exactly we do is we have a beaker, and then we add these sort of molecules of zirconium chloride, which therefore and then the terephthalic acid as the organic linker. We add some solvent and then put it into oven. After that, we wash and dry these sort of morph materials. They would look like white powder, and then we need to look at whether we are doing any post modification with it. Are we adding other elements onto it? So that would be things that we do. It's quite similar to the A-level, the teaching lab in A-level, where you kind of grow crystal of copper sulfate, for example, and then you also have to wash and dry the compounds. It's just that these sort of compounds are no longer binary compounds. Like you have one metal and one anion, one cation and one anion. It may be way more complicated. In our other people in our same research group may deal with other materials, which also involve these sort of mixing different chemicals together and then put them into an oven and wash and dry. They may be perovskite materials, so some very fancy, complicated metal oxide, and which is apparently is very good for catalysis. And then I would show some of my data. These are actual data to tell you what exactly is what would we be able to measure, and then what characterization that we need to do in order to kind of be able to tell the story of what is happening. So for example, in this case, I did the photocatalytic water splitting on this. So previously, this is the morph, the metal organic frameworks with the amine group on it. And then these 4 are different loading or different proportion of cadmium sulfide, which is a semiconductor that I have added onto my morph. So this is the rate of photocatalytic water splitting. What I have done is I have put everything in the beaker, shine light onto it, and then for 1 hour, and then I check how much hydrogen is present in my beaker. So of course, it's quite a complicated beaker. So not the sort of beaker that you use in the teaching lab of the A-level experimental course. Now, I found out that there is an optimal kind of point that I can add to in before it. If I add even further more of cadmium sulfide, it actually doesn't give a very good rate. But at 1.8% of cadmium sulfide, I would be able to get very good results on catalytic activity. So then I will need to do some characterization in order to explain what exactly is happening inside this system. So for example, one of the structural characterization that is very frequently used is the X-ray diffraction. It involves the different planes of atoms, and then basically these sort of different planes of atoms will give you a peak in this X-ray diffraction. And all of these samples give very similar peaks. So it shows me that the structure of these samples doesn't really change. And as a result, it's a good thing because we don't want my structure to collapse after adding the cadmium sulfide. Otherwise, there would be no point of me using this sort of morph as support. And then other structural characterization is I picked this one because it's kind of the most obvious in one sense. You are zooming to very, very close and to see exactly what it looks like, taking a very tiny photograph of what your samples look like. So these octahedral stuff quite kind of look like octahedral. These are my morph materials, the metal organic frameworks themselves. And then there are some cadmium sulfide. This is the cadmium sulfide. I think these are the cadmium sulfide that are deposited on the morphs. For this sample, these two samples, they both consist of these sort of darker spots. So what other
Bryan,
things?
sorry,
yes.
Sorry to interrupt. I just had I was about actually to say we've just had the first couple of questions in, but which I'll chair for you at the end. But actually, then we've had another question, which is specific to what you've just said. So the question is, why the jump from 0.2 CDS to 1.8 CDS? Was there a reason? Values in between weren't tested, or were they just omitted from the graph?
Yes. So these are actual data. So let's just go back to the data. So for example, there is a change in data. These sort of values are the amount of hydrogen we measured, right? So going from 0.2 to 1.8, yes, there is a big jump. Why is there a big jump? That is what we need to do in order to find out that what we do is the structural characterization. So there are a lot of potential structural characterization techniques that we can do. Some of which I didn't show because they can be quite complicated, but some of them I have shown here. So the X-ray diffraction, as I previously mentioned, and then the TM images. So we mentioned that there are darker spots over here and here.
And one more interruption, just to say, if anybody's got any more questions, whether they're ones as we go along for Bryan or for the end, which I've got a couple ready for you later, Bryan, please do ask away in the Q&A tab. Thank you.
Yeah. Thank you. And then these sort of darker spots, how am I able to tell what these sort of darker spots is? There is another technique called this energy dispersive X-ray images. This is from the 1.8 samples, I think. So this is a very blurred microscopy image for whatever reason. They may be out of focus or whatever. But the most important thing is that we kind of see these sort of darker spots. And this technique available, it makes us able to see what element is constituting to that pixel here. So for example, we see 5 darker spots on this TEM image, and then we go to cadmium and sulfur absorption edges and see they correspond well to these sort of darker spots geometrically. And therefore, we can kind of draw this conclusion of cadmium and sulfur being the identity of these sort of darker spots that are present on the surface of the morphs. And then also there are some sulfur and cadmium that are isolated, that are not really related to these darker spots. However, they may be kind of diffusion into the pores instead of being reacted and then forms on the surface. And then there are other measurements that we can do. This is called a BET surface area. Basically, we take a very porous materials, we try and put nitrogen gas into it and see how much it can absorb in order to calculate that surface area that is present in these samples. And then these are the samples that we ended up. These are the data. So we have a very good correlation with the 1.8 and 2.3, where you have the optimal point on the 1.8 sample, and then less so in the 2.3 samples. And for example, with these sort of data, we can kind of briefly conclude that you have the cadmium 2+ and the sulfur that diffuse into the pores. And then also, there are the cadmium sulfide that is formed on the surface of the UL66NH2, which is the name of the MOFs. And what we can see that it's the interface between the cadmium sulfide and the UL66NH2 that is enhancing the catalysis. We did some other characterization techniques such as X-ray absorption spectroscopy, which tells you the coordination environment of cadmium inside. And then we also kind of analyzed the particle size of the cadmium sulfide from the microscopy images that I previously shown in order to reach these sort of conclusions. So this is the sort of things that we do. So we do some synthesis, we do some catalysis, and then we do some characterization, and then tell the story of what exactly is happening in these systems. And then if things go well, we will write these sort of data up, and then we will publish these sort of data. Yes, any questions? That would be the end of my presentation.
Thank you very much indeed. We have a couple of questions already. I'm going to go to the ones that came in already before that really specific one based on the content. Okay, so go back in time. Can you recommend anything you read or saw before university which inspired you in chemistry? And I guess this links in with the supercurricular mentioned at the start. Anything you'd recommend supercurricular?
I wouldn't recommend anything specifically, because unless you have a very clear vision of what you want to do. For example, if you really, people say if you really want to become an artist, then maybe that you would be able to plan ahead yourself. Oh, I need to go and go to these sort of museums and then watch things. But generally, more likely, just like when just like the myself, I don't know, 10 years ago, just in secondary school, I'm quite unsure of what exactly I want to do. And my advice in that case would be to try everything that is possible. So including there must be some sort of extracurricular or supercurricular activity available in the secondary school, in your environment, your education environment. And that's how you kind of get more exposure in order to be able to judge what exactly you like. So of course, including being in the talk today, it's great that you gain more exposure. That would very much help to slowly shape, and you would get a clearer understanding of what you really want to do, for example, in university, very gradually.
So I suppose that's really super curricular interests, like whatever you're into, or you don't even know you're into yet.
Yeah,
doing it for the sake of working out whether you're into. Okay, second question for you, Bryan. What would you like to do with your PhD? Where's the future for you from here?
It varies. I am still looking around. The majority of the PhD students graduate, and then they would go to maybe some consulting companies, or maybe the financial industry, or maybe the chemical industry. So there may be people, for example, to make medicines. So a very random compound that happen to have some effect from some studies. There must be people who know how to make those compounds and be able to make certain chemical bonds are very difficult and require a PhD. So that may be something that they recruit PhDs to manage. Alternatively, the PhD students are known to possess some sort of analysis skills, because they have to manage their own project and they have to analyze in depth what they are doing. And these may be necessary or useful skills in consulting companies, because they also have to research in, for example, a certain industry, and they may need to interview with experts in order to be able to say, overview of a certain industry, for example, the fuel industry or the plastic industry, for example. Yeah, so that very much depends.
So in other words, not just staying in an academic world with a PhD, very much going into industry potentially too. Yeah.
Yeah. So there are a lot of possibilities for PhD students. So I don't actually think you absolutely have to stay in academia.
Great. And then a question that takes us straight back into the chemistry. What type of imaging was used to identify the cadmium and sulfur? Was it the same electron microscopy or something else?
What we have done is called transmission electron microscopy. So electron microscopy just means things that are being fired. Because for example, in biology classes, you guys may have seen those sort of the small microscopes. Those are optical microscopes. So things that are being passed through your samples are light. Of various intensity. But things are quite small in the chemistry world. So what we need is electron microscopy. So we fire electrons instead of light. Because their energy is higher, therefore they can give you more better resolutions to stuff. This transmission electron microscopy just means that the electron is transmitted instead of being scattered, or there are maybe other methods of microscopy that I am unfamiliar with. So what we have done here is transmission electron microscopy.
Great. Now a final appeal, please. Any more questions for Bryan? Bryan, thank you so much for your passionate discussion of what you've been taking us through tonight. It's a really in-depth examination of exactly the sort that we were talking about earlier, in terms of just go deep into something, and I know people who have been are not able to join us in person tonight will be looking forward to watching this online too. So thank you very much. It looks like there are no further questions. Thank you also to our guests for joining us this evening, and enjoy the rest of your evening. Thank you very much. Goodbye.
Thank you. Goodbye.